Welcome back, scholars. Today we're going to dig into the unit circle and determine the coordinates of various points on the unit circle using special right triangles. Let's get started. Let's start by taking a closer look at the unit circle itself. A few key features I'd like to point out are these points in red along each of the axes. If I were to draw a segment from the origin out to any of these points in red, it would have a total length of 1 unit, or more specifically, a radius length of 1. A circle with a radius of 1 and whose center lies at the origin is referred to as a unit circle. Its equation, in fact, is x squared plus y squared equals 1. To that end, a unit circle is analogous to the concept of a parent function. So what's next? Well, we'd like to use these known characteristics of the unit circle to give the coordinates of any point on the circle. Let's put our focus on this blue point labeled with the ordered pair x, y. To find those coordinates, we'll drop a line perpendicular to the x-axis from that blue point down to the axis itself. We'll also draw a horizontal line out to that point of intersection. In doing so, I've created a right triangle. We'll call its inner angle theta. We can also think of theta as a central angle which intercepts arc S along the unit circle. Remember from geometry that an arc intercepted by a central angle is equal in measure to that angle. Okay, other interesting facts to note. The base of the triangle is equal to the distance from the origin on the x-axis. Similarly, the height of the triangle is equal to the distance from the origin on the y-axis. So let's put this to use. Suppose that our angle theta now is 45 degrees or pi over 4. What will the coordinates x, y be when the terminal side of this angle intercepts the unit circle? Well, we know the radius shown in black is 1 because we're working with a unit circle whose radius is 1. We also know that right triangles with an acute angle of 45 degrees are isosceles. That means that the base equals the height. The ratio of the side length to the hypotenuse in a 45-45-90 right triangle is 1 to the square root of 2. Since the hypotenuse is 1, that means each leg will be 1 divided by the square root of 2. I'll take just a moment for a detour here. We'll need to rationalize the denominator of this fraction to write it in simplest form. Remember that to do so, we'll need to multiply by 1. In this case, that 1 takes the form of the square root of 2 over the square root of 2. Simplified, we get square root of 2 over 2. Very nice. Now we know the coordinates x, y will be square root of 2 over 2 and square root of 2 over 2. What if I asked you for the coordinates of the points at 3/4 pi radians? That would be somewhere over here, off the screen a little bit. Think about your reference angles. We can draw the very same right triangle reflected out in quadrant 2. This time you'll need to keep in mind that the x coordinates in quadrant 2 are negative while the y coordinates are still positive. Before we go, let's quickly recap the details of our 30, 60, 90 triangles. If our bottom left angle is 30 degrees and our hypotenuse is 1, then the shorter leg, that is opposite the 30-degree angle, will be 1/2, while the longer leg, which is opposite the 60-degree angle, will be 1/2 times the square root of 3, or written as square root of 3 over 2. If we switch it up so that the 60-degree angle sits at the bottom left, it's the same triangle, but the base and the height are swapped. Okay, that's it for now. In our next lesson, we will add in our trig functions sine, cosine, and tangent. For now, practice filling in the coordinates for all of the key points along the unit circle. See you next time.